welcome once again. So, to the course Metallocene and Metal-carbene based organometallic compounds for application in polyolefin catalysts. If you remember, in the last class we discussed about the bonding, started the discussion about the bonding in Metallocene compounds, and you saw that the Cp or ligands, how they can undergo the pi orbitals of the Cp, how it can undergoes the LGO to form the set of LGO orbitals of different symmetry, which can then interact with the specific d and s and p orbitals of the metal with the symmetry matching. So, and that the way we can construct the molecular orbital of the ferrocene, and this is essential to understand the property and the structure, because if we understand the bonding very clearly, then it will be very easy to understand the reactivities of that particular metallocene. So, it is we started discussion with a simple example of a parallel metallocene with a parallel Cp ligands, which is like ferrocene. You know that ferrocene we discussed extensively in the last class, that in the ferrocene the Cp ligands are like parallel, and it can exist as in two forms, eclipsed and staggered. In gaseous phase it actually exists as as eclipsed, and the energy barrier between the eclipsed and staggered is very low, only 4 kilojoule per mole. So, it can undergo the rotation, okay? And that is why you see in even the proton NMR, you will see a single signal of the Cp rings in the ferrocene. Okay. So, we will take a simple model of ferrocene we will discuss with a eclipsed form, and we will try to understand that how the molecular orbitals can be constructed. Let us start, and then we will discuss with the help of the molecular orbitals what are the unique properties of the metallocene compounds, which is this will be very useful for to understand the mechanism of the metallocene catalyzed polymerization. Okay, so, concepts covered, we will try to understand the bonding in metallocene using molecular orbital theory, and then we will try to understand the electronic nature or the unique properties of the metallocenes. Okay, so, key points will be the molecular orbital theory and the different polyonyl ligands, how they behave. Okay. So, this one we started discussion. I will just recap few important points, that these are the pi orbitals of the cyclic polyonyl ligands. Here it is cyclopentadienyl ligands. So, you will see that sigma, that is the one is the lowest orbitals, this one, this is where there is no node. Okay. So, this is and the little bit at higher energy, there will be degenerate system, where you will see there is a single nodal plane. Here you will see this is 1, this is 0 nodal plane, this is 1 nodal plane, and after that you will be another, there will be a single one degenerate set of orbitals, where you will see 2 nodal planes. And then what we will have to do, we have to do the LGO operation, that is in the case of multiple Cp ligands, as example for ferrocene we have a 2 Cp ligands, 1 and 2. So, these 2 Cp pi orbitals of the 2 Cp ligands will undergo the LGO, and through the addition and subtraction of the particular symmetry, like this one, you will see that this is with the sigma symmetry, and how we are the symmetry with the base with the basis of that, how you are looking from the above to the down. Okay. So, like here another way to draw this one, simple approach. So, it will be like, so here it will be you see that if from the above how does it look like. So, you will see plus 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 plus, okay. And from here in this case it will be like that, and this case it will be like that. Okay. So, plus minus, and here also like this one like that, and here also it will be like that. Okay. So, this is the symmetry with respect to your how we view from the top to down. Now, this is the sigma, this is the pi symmetry, this is the delta symmetry. Okay. Now, what we will do? We will do the addition and subtraction from of the each set of orbital, and we will get the LGO orbitals, and we will try to match with the metal orbitals. Okay. And then the way we will form the molecular orbitals of the in the metal Sp2 complexes. Okay. Where I am considering a simple system where 2 cyclopentadiene ligands are there. Okay. Now, let us start it. Okay. So, as you know that this A1, if you do the addition and subtraction of this one. So, I am doing first addition. Okay. So, what you will get? You will get 2 set, that is one is A1G, okay, and one set you will get the A2U. Okay. Okay. I am sure that you know that what is AET. A is basically single orbitals, E means double degenerate, T is triple degenerate. Okay. 1 and 2 is based on the symmetry, how does it with respect to principal axis, and G, U are the parity. Okay. So, if you have forgotten, you can just take a look how we do the Millikan term symbols and how we use the symbols to to designate the orbitals with respect to the symmetry. Okay. Okay, fine. So, this one you will see A1G and A2U. So, how does it look like? If you do the A1G, that means the symmetry you will see that this lobe, okay, let us say this is plus, okay, this is plus, this is plus, this is plus, this is plus. Okay. So, here also plus, so plus. So, if you do the addition, okay, then it will look like this one. Okay. And this one you see that this is perfectly can interact with the 2 orbitals of the metal. Can you tell me which those 2 orbitals? Okay. We will consider in the let us say like 3D transition metals, like this kind of 3D transition metals where metal is let us say iron, cobalt, nickel, copper, titanium, vanadium, like that. So, here you will have a 3D, okay, 4s and 4p, and you all know how this s, p, d orbitals looks like. So, if you can see this one, okay, and in more easily we can, I mean very simple way we can also draw like this one, okay, this the LGO after the addition of this orbital, that is the lowest energy orbitals with sigma symmetry. So, how does it look like? It will look like this way. So, this one and you see this one. So, this is plus, this is plus. Okay. So, this is the addition, okay, of this sigma symmetry pi orbitals. Now, you can imagine 2 orbitals of the from the metals. One is the dz square obviously, okay, and another one, can you guess? Yes, s orbitals. Okay. So, this would be 3D of course, and this will be 4s. So, you will see this orbital can interact with the 3D and 4s orbital of the metal center. So, we have how many orbitals? 3d 5 orbitals, 4s 1 orbitals, 4p 3 orbitals. And what we will do now? We will be basically matching the symmetry, okay, no matter the what energy it has, that we will consider after later. That definitely that there is a role, because you know that two issues you have to consider. One is the symmetry matching, that is very important, okay, and another one is the energy difference between the two orbitals which will undergo the interaction. So, if the energies are similar, then definitely there will be good interaction if it satisfies the symmetry, and if the energy is much difference, then there will be weak interaction. So, the bond strength obviously will be lower. So, that two issues we have to consider. First, let us consider the symmetry. Okay. Now, this is fine. So, here you will see this is a bonding or overlap. So, this is if you consider the eclipsed. Okay. So, what you are getting? You are now I am getting a set of LGO orbitals which can nicely interact with the 3d and the 4s orbitals. Okay. Now, how does it look like if is a subtraction? Okay. So, subtraction will look like this one. So, this is my this one. Now, can you tell me that which metal orbitals it will interact, okay, with the symmetry or by satisfying the symmetry? Okay, yes, this is. So, this is, if we consider that is the z axis, okay, and this is x and this is y, then yes, definitely. So, this is my pz orbitals. Okay. So, 4 p z orbitals. So, you will see that this orbitals is perfectly matching with pz orbitals. Okay. So, it is easy, okay, not difficult. Now, let us go to the another set of orbitals, that is the this set of orbitals, okay, this set of orbitals, okay, with pi symmetry, that is one single nodal plane. Now, here you first consider the addition. Okay. So, this addition, how does it look like? How the LGO, the resultant LGO orbital look like? So, let us see this one. Okay. If I draw in a very simple way, okay, then we can draw it like this. Okay. So, we will draw like, okay. So, this will be minus plus, and this will be the lobe, okay, phase. Now, you see why I have drawn, you see this nodal plane. So, this is the, if you consider this is plus, okay, and if you this consider is a minus, okay. So, same will be the bottom also, because I am doing first addition. Okay. Now, can you tell me that which metal d orbital will be perfect, okay, for this orbital, okay, for the interaction? Okay. Can you guess? Yes. So, this will be nice for the if you consider this is the x axis, this is the x axis. So, px orbital will be fine. Okay. So, I will show in a different color, so that you can understand easily. So, this will be the so this is px, that is the 4 px obviously. Okay. So, you will see that px orbital will be perfectly matching. Now, you have the another, so two orbitals, 2 pi orbitals. So, similarly, this one also will undergo LGO. So, another set of or LGO will be fine with py if you see the symmetry. Okay. Fine. So, now you will see that this E1 orbital, that is the after addition, that E1 set of LGO orbitals will interact with px and py orbitals of the metal center. Now, consider how does it look like if there is a subtraction of these orbitals, to that is the how will be the resultant LGO. So, we will draw like this simple way, okay, and we will do the like that. Okay. Now, it is easy, okay, to guess that which orbital will be matching, which metal orbital will be matching with this LGO orbitals. Can you guess? Okay. Yes. So, this will be fine for the XZ orbital. So, I am drawing with different color. So, this is the XZ orbital. So, I am writing here. Okay. So, let us say 3D XZ. Okay. So, you will see that. So, this E1 set of LGO orbital will be fine with the 3D XZ. Now, I told that is another orbital in the same set. So, that will be so that LGO will be fine with 3D YZ. So, XZ and YZ gone. So, you will see that from here my DS orbitals is done, the DZ square done, and XZ YZ done, PX and PY done. Okay. Fine. Now, left over is the 3D XY and 3D X square minus Y square. Okay. Let us try to find out. Okay. Okay. Fine. So, let us find out the E2 orbitals and how does it look like. With this is with the, as I told, sigma symmetry, this is the pi symmetry and this is the delta symmetry. Okay. So, I will, this is the sigma symmetry, this is important, okay. This is delta symmetry. Okay. Now, how does it look like? First we consider the addition, okay, and it will look like okay. This is little difficult to imagine, okay, and okay, and this would be okay, fine. So, this is the addition. Okay. Here I, in all the cases I have shown it is, this is the addition, here also addition, and here I am showing the subtraction. Okay. Here also subtraction. So, first is addition. Okay. Now, can you tell me that which orbital will be perfectly matching with this symmetry? Okay. So, this one. So, here you see this plus plus minus minus. Okay. So, let us draw the orbitals. Okay. And this is, so this is plus 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 minus. Okay. So, if you see that this is the plane xy plane. Okay. So, this is the xy plane. So, this is nothing but the 3D xy. Okay. Now, if you consider the another orbital of the same set. So, this would be fine with 3D x square minus y square. So, now you will see that my 1, 2, 3, 4, 5, 5 d orbitals are now done, px, py, okay, 2 orbitals and done. Now, here dz square, here s orbital done and where there 4 pz, so 3 orbitals done. Okay. So, 5 3 8 and 1 9 orbitals from the valency shell. Okay. So, how the subtraction looks like here, and you will see there is the subtraction will look like, first you draw it like that. Okay. Now, here you see and okay. So, yes, so here you see that there is a difference here, you see plus minus minus plus 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 minus minus. Now, this is little different, this one for this symmetry, this LGO, okay, no matching orbital, no matching metal orbitals. Okay. So, here you will see that this is from the E2 set, this is the bonding. Now, we now understood that how the metal orbitals can interact with the resultant LGO orbitals. Okay. So, this is clear now. Okay. So, we have now A1G set, okay, A1G set, A2U set, that is the A1G, this is the A1G, this is the A2U. Okay. Now, we have the set of E1U, E1G, that is from the sigma symmetry LGO, that is the pi symmetry LGO, and we have the E2G and E2U, that is the delta symmetry orbitals. Okay. Now, you see that from here this is my sigma, this is pi, and this is the delta symmetry LGO. So, here you will see for this one we have a metal orbitals, this one we have metal orbitals, this one we have a metal orbitals, but this one there is no matching d orbitals. Okay. Now, let us do try to construct the MOT, that is the molecular orbital with the help of molecular orbital theory. I am sure you know that what is the molecular orbital theory. There is three major main theories to explain the bonding, that is the VBT, valence bond theory, one is the molecular orbital theory, okay, and we also know that ligand group orbitals, that is also, or LFT ligand, that is also useful to explain the bonding in transition metal complexes and organometallic compounds. Okay. So, let us discuss. So, this you all know that we know CFT, crystal field theory, where we only consider the electrostatic interaction. Molecular orbital theory, we basically consider the covalent nature, and LFT is basically combine the crystal field theory and the molecular orbitals. Okay. So, these are the main theories to explain the bonding in transition metal complexes and organometallic compounds. Fine. Let us try to consider try to construct the molecular orbitals of ferrocene. Okay. Let us now we have the set of the LG orbitals which can interact with the metals. Okay. So, you see here in this case. So, this is the relative, this one is the 2 CP ligands, this is basically the all the these are the LGO, okay, what we learnt from the last 2 slides, and this is the Fe, and as I told, this is the 3D, this is the s orbital, that is the 4s, okay, and that is the 4p orbitals. Okay. Now, it is very interesting. Okay. Now, we have this set of orbitals. Now, we know that this symmetry and this symmetry. Now, what this symmetry we know, okay, you consider the symmetry and the notation, okay, here, that is very important, okay. And we also see that relative energy, okay. So, here you will see that this one, okay, this one, that is the A1, A2, A2 symmetry LGO orbitals are much lower in energy compared to the A1, A2 atomic orbitals of the metals. Okay. So, these are basically the atomic orbital this side. The left side is basically atomic orbitals of the metal, and the right side is the LGOs of the two CP ligands. Now, if you match with respect to the symmetry of the LGOs, you will get this kind of molecular orbitals. Okay. So, here main important is the is here. Okay. What you are getting from here? So, this is the E2, that is okay, and then you are getting the A1, okay, and then you are getting the E1. Okay. In several books they also write E2G. I am just writing in general. So, you can also write E2G, A1G and E1G. This is basically anti-bonding. Okay. So, this is actually anti-bonding, this is actually non-bonding, and these are the bonding. Okay. We no need to consider this area, because these are quite in high in energy. The electrons will not be occupied in these orbitals for the 3D transition metals or 3D and 4D transition metals. Okay. So, few points you have to consider here. Okay. Some of the points, very important points. So, here very important point, this will be very helpful later. So, here you will see that in this case, here you will see that A1, A2 is much lower in energy. Okay. This one much lower in energy compared to the atomic orbitals. Okay. So, that is why the A1, okay, A1G orbital of Cp, here Cp means Cp minus, we generally call it just a Cp, okay. But actually it is cyclopentadienyl, that means Cp minus of Cp is very stable due to the mismatch in energy. Okay. And for that reason, the interaction between the metal center, metal orbital and the ligand LGO of the A1G LGO is very less, and that is why is Cp minus. Okay. This you have to understand that Cp minus is a very poor sigma donor. Okay. Cp minus is a very poor sigma donor, and what is the reason? Because the A1G LGO is very much stable. Okay. And you will see that energy difference between the A1G symmetry LGO and A1G symmetry of the metal orbitals is quite different. Okay. Now, another interesting point is that E2G, okay, that E2G, okay, is high in energy. Okay. So, here also interaction is little, fine, and for that reason this Cp minus ligand is not good pi acceptor. So, Cp minus is neither a good sigma donor or nor a good pi acceptor. Okay. And the reason is very clear from the molecular orbitals. Okay. So, another few features that E2G, okay, and A1G, E2G and A1G, okay, that is this one and this one, okay, are slightly bonding in nature. Okay. And also E1G, that is this one, okay, because you see that if electron I have to take from the metallocene, the electron will come from the A1G. Okay. And if I want to put one electron in the on the metallocene, that means I want to reduce the one metallocene, that electron will come here E1. Okay. Now, E1G is also not okay, good, not significantly anti-bonding. Okay. And this is due to the mismatch in energy. Now, what will be the impact of this one? So, the impact will be that as this E2G and A1G, okay, are not really is a very true in true sense is not really a bonding orbitals. So, what will happen if I take electron, that is if I oxidize the electron, oxidize the metallocene, if I take one electron, then if you consider the stability, that stability difference will be not really dramatically change. So, that means you can oxidize the metallocene and also reduce the metallocene. Why? Because the E1G is not significantly anti-bonding. That means, if you put one electron in the anti-bonding orbitals, then also the stability will not be like a very different. But yes, obvious, if your all the bonding orbitals are filled and there is no electron in anti-bonding orbitals, that like ferrocene, okay, which satisfies the 18 electron rules, that will definitely the most stable, and that is why ferrocene is the most stable. Here you will see, okay, that 1, 2, 3, 4, 5, 6, 7, 8, 9, the 9 orbitals, that means 9 into 2, 18 orbitals, okay, and there is no electrons in the anti-bonding orbitals. So, here the ferrocene, that is why very stable in nature. Okay. So, you see the from the molecular orbital diagram, molecular orbital theory, you can get lot of information about the electrotic nature of the metallocene. Okay. So, if you now consider like the all the interaction, so the best interaction is, and why I am telling the best, because this actually dictates most of the properties of the metal centers, that is the E1G plus the 3D. And you, if you see the last slide, okay, that the E1G, that is the this one. Okay. So, this the orbitals from the pi symmetry, okay, that is the this one, okay, E1G, this actually mostly dictates the electronic properties and the stability, because this is the best match. Okay. E1G 3D interaction is the best match for the ferrocene like metallocene compounds. Okay. So, in summary, in the molecular orbital diagram of ferrocene like metallocene, you will see that this is the most important, these orbitals are the most important because it actually dictates the electronic nature of the metallocene. Like as example, like if you see that Cp2, okay, ferrocene, okay, I just told that this actually 18 electron system, okay, okay, and you see that how if you fill up the electrons, how you can fill up. So, you will fill up like E2 4 because all bonding orbitals will be filled up. This is the slightly anti-bonding in nature. So, E2 4 A 1 2 and here E 1 0. Okay. Now, here you will see, so here these are all the non anti-bonding orbitals are filled up. Now, if I oxidize it, okay, what will happen? Now, 17 electron system and you will get E24 A11 E10. So, what I am trying to say that although this is 17 electron system, so it should be definitely less stable, but what I am telling that you can prepare, okay, by oxidation chemically or electrochemically to Cp2Fe plus, and this you can synthesize it or you can get it because your we are taking one electron from the orbitals which are not really 100% bonding in character, and that is why actually we can synthesize this 17 electron system. Now, similarly, if you consider the cobaltocene, this is 19 electron system. Okay. So, definitely this is less stable than the ferrocene because it has a 19 electron system, but what I am trying to tell that you can prepare it, okay, the cobaltocene, okay, because if what we are doing compared, if you compare with the ferrocene molecular orbitals, then we are basically putting one electron here. Okay. As I told that this is not really kind of a true anti-bonding orbital. So, that means there is not much sacrifice in the stability. Okay. So, this is the main features in the metallocene molecular orbitals. Okay. Similarly, you can also prepare the nickelocene where it is 20 electron system, and what will be the electron arrangement. Okay. So, like this one, like this one. Okay. So, very easy. Okay. So, if you also you can get lot of information from here. One as example, like here you see unpaired electron, I am writing UE unpaired electron. So, here you are getting unpaired electron is 0, here you are getting unpaired electrons 1, here you are getting unpaired electron 2. Okay. So, these are interesting. Okay. You can get lot of information, electronic nature, the stability, the orbitals which are important to understand the reactivity and the structure property relationship. Okay. So, as I told that whatever we have discussed so far in the molecular orbitals diagram, we have discussed for the this kind of category B metallocene where the two Cp ligands are parallel, and we will be mainly interested for bent kind of metallocene. Okay. The bent metallocene, that will be our interest, because this is also another unique features compared to the metallocene compounds where your Cp ligands are in parallel. Okay. And here you will see these are bent, and these L can be 1, 2, 3 like that. So, the L number of L's, okay, number of L's I am telling, this may be 1, 2 or 3 depending on the valency electrons of on the metal. Okay. So, this is very unique and there are a lot of applications in various organic synthesis, mostly catalysis. Okay. There are a lot of applications on these bent metallocenes. Okay. So, that we will be discussing in the next classes. Okay. So, you will see that how this bent metallocene due to some unique features are plays a vital role in not only in academics, but also in industry, where we routinely use the bent metallocenes like this kind of things in catalysis in organic synthesis to synthesize value added products, commercial products. So, that will be really interesting. We will try to combine the electronic nature, the orbitals, and try to understand its reactivities and mechanism to have a very clear concept. Okay. So, we will discuss continue discuss in the next class. So, as a summary, what we have learned in this today's class. So, we now understood the molecular orbitals, okay, molecular orbitals of metallocene with one simple example of ferrocene, where two CP ligands are parallel. Okay. We will try to understand the electronic nature of the MO and the stability of the metallocenes. Okay. So, the majority of our discussion from this class has been you can read from the Crabtree or the Hartwig books. So, thank you, and we will again see in the next class, and the next class we will try discuss more extensively about the bent metallocene, the unique feature, electronic nature, and the reactivity studies, and then we will enter to the catalytic polymerization. Thank you very much.